Okay, even in distilled water, we still have an existing hydronium and hydroxide population. Water can autoionize itself. What that means then is if we can imagine if we have two H2Os that are reacting with each other, then what they can do, and this is an equilibrium situation, they don't do this. This is a heavily reactant-favored reaction, as in not very many of these products get created, but they can naturally have one of the waters act as an acid and the other water act as a base and donate the hydrogen from one to the other and end up with hydronium, and then the donator is left as hydroxide. So this is called autoionization of water, and these populations get created naturally even when there's no dissolved particles in the water at all. The concentration that these things will build up in distilled water at some, I don't know, 25 degrees C or something, some normal temperature, is 1 times 10 to the negative 7 molarity. So very, very little for both. What that means then is that if we were to come up with the equilibrium expression for this, which has a special name, we call it Kw, it would be equal to, these are both liquids, so neither one of them enter the expression. But since these are both aqueous, they both do. The concentration of the products, H3O plus and OH minus. Kw is 1 times 10 to the negative 14. This is at, I don't know if it's 25 degrees or some normal temperature. This would depend on temperature. This process would be an endothermic process, meaning energy would have to go in to the two water molecules to cause them to exchange their hydrogens. And if we think about Le Chatelier's principle then, what that means is if we added energy to the system, or if we make it hotter, we will create more H3O plus and OH minus. If we think of Le Chatelier's principle, as we make it hotter, we add energy, so the system will respond in a way that tries to correct or go back to the old system or resist the change. And so if we add energy, it'll try to use up the energy, favoring the forward reaction. What that means then is that as temperature goes up, the Kw will also go up. This can also be related to pH. Recall that pH is equal to the negative log of the concentration of H3O plus, and pOH is equal to the negative log of the concentration of OH minus. If we take the fact that the concentration of H3O plus and the concentration of OH minus at Kw in normal temperature is 1 times 10 to the negative 14, and then we take the log of both sides, then we get the value negative 14 over here. And over here, one of our properties of logs is that log AB is equal to log A plus log B. So we can take advantage of that and split this log into log H3O plus and plus log OH minus. And then if we multiply this whole equation through by a negative 1, I would get negative log H3O plus and negative log OH minus, and that would be 14. Don't mix those up. And Now we can go back to the fact that this is the expression for pH, and this is the expression for pOH. And so we've been using this in a few videos before, and we talked about this all the way back into grade 11, but that's how we know that pH and pOH has to add to 14. It's really a result of the kW of water. If the temperature was much higher, and so the kW was different, pH and pOH would add to something different. But we use this expression pretty universally because kW doesn't change that much as the temperature changes. So, with just water, no particles in it, the water can act as an acid and some of the other water can act as a base. One water can donate a hydrogen to another water. That creates hydronium and hydroxide. And then that hydronium and hydroxide will naturally populate in distilled water at a normal temperature up to 1 × 10⁻⁷ molar. Using that, recognizing this is an equilibrium, we can write the equilibrium expression and come up with the Kw, or the equilibrium constant for pure water. And exploiting that with a little bit of mathematics, we can come up with our equation pH plus pOH equals 14, which we use if we want to calculate the pH of a base, where we will calculate the pOH first and then use this expression to determine the actual pH of the base.